Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over part 5 of our work on applications of differentiation. This is tailored following section 3.1 of the Larson's AP Calculus texts, problems 17 to 19. The instructions are for us to find the absolute extrema of the given functions on the closed intervals. To find the absolute extrema of the functions that we're going to be looking at, we're going to be using a strategy called CVEPS check. Okay, so to find the absolute extrema, when we're talking about absolute extrema, we're basically talking about the absolute minimum or maximum. Okay, we're going to be using something called CVEPS check. Alright, so what does that mean? Let's go over what that means real quick. CV basically represents your critical values. Okay, and to find your critical values, these are basically where f prime of x is equal to 0 or f prime of x does not exist. Okay, so there goes your critical values for CV and CVEPS check. E represents endpoints, okay, for the closed intervals. In this particular problem set, we're going to be looking for absolute extremas on closed intervals. If a problem is on an open interval, then this E component is not applicable. Alright, so let's say you're dealing with endpoints on AB, for example. Your endpoints will be x equals A and x equals B. Those will be the endpoints. P basically represents potential extremas. Alright? What are potential extremas? Potential extremas are basically the combination of critical values and endpoints. Now, if you have an endpoint or a critical value, it doesn't automatically mean that those are extremas. You have to do the next part, which is the Sine Chart. Alright, so S represents Sine Chart. Alright, so this is where calculus comes into play. We're going to make use of our calculus tools to determine the behavior of the function around the endpoints and the critical values. Of course, you use calculus for the critical values components too. So for the Sine Chart, when you think about Sine Chart, think about the fun chart. Okay, the fun chart is basically a nice organizational tool that helps you see the connection between the signs of f prime and the behavior of f, and the signs of f double prime, and how it impacts the behavior of f prime and f. Okay, so for fun chart, you have f, fun, concave up, concave down, that's the fun part. F prime, increasing, decreasing, and then over here, increasing, decreasing, and then plus, minus, and then f double prime, plus, minus, and over here there is no connection. So what does the fun chart tell us? Well, it just basically tells us that when f is concave out, f prime is increasing and f double prime is positive. If f is concave down, then f prime is decreasing and f double prime is negative. You can go in any direction that you want. Okay, so for example, f double prime is positive, that means f prime is increasing and f is concave up. In the second column here, it just basically helps you to see the connection between the signs of f prime and the behavior of f. If f prime is positive, f is increasing. If f prime is negative, then f is decreasing. Alright, so that's the S component of CVEPS check, and then the check mark just basically is to check. Alright, so just this is arithmetic components that you use to verify the extreme values. Verify the extreme values. We're going to be using the original function to verify that the extreme values that we came up with are actually the extreme values. Alright, now let's take a look at the first problem, problem number 17. Let's say we have the function f of x equals 4 minus x over 3, and this is on the closed interval negative 2, 3. Alright, so that's the function. Solution is as follows. What are we doing here? We're to find the absolute extrema. So find the absolute extrema. Basically the max or the min. Alright, so when we're finding the absolute extrema, we're going to be using CVEPS check to carry out this task. Alright, so we're going to break it down. 1, 2, 3, 4, 5 components. Let's start with the first component. Part 1 is the CV part, which is to find the critical values. Okay? So to find the critical values, what are we going to do? To find the critical values, we're looking for where the function f prime of x is equal to 0, or where f prime of x does not exist. Alright? Let's do it. So starting with the original function, this is a polynomial function, okay? What do you think the answer will be when we're looking at f prime? Are there any points in this polynomial function where the derivative is non-existent? The answer is no. Okay, you have to remember that polynomials are smooth and continuous, so anything that causes the derivative to be non-existent, namely corner cusps, vertical tangents, or discontinuities, cannot be found on polynomial functions. Alright? Okay, so f of x, this is f of x. Let's find the derivative. F prime of x basically involves finding the derivative of these two components. So the derivative of 4, and then you can factor out 1/3 and focus on looking for the derivative of x. Alrighty. Now if we carry out the computation, we're going to have f prime of x equals 0 minus 1/3 times 1. So 0 minus 1/3, derivative of x is just 1. So we're going to have negative 1/3 as f prime of x. Alrighty. So we have a constant derivative or constant rate of change at every point in time in this function. So where is f prime of x equals 0? F prime of x is constantly negative 1/3. It is never equal to 0. So there's nowhere where you have f prime of x equals 0. Remember, when the derivative is 0, you have a horizontal tangent line. Now, where is f prime of x non-existent? F prime of x is always defined, namely negative 1/3. Okay, so there is no point where we have a non-existent derivative or where the derivative does not exist. Alright? So that's that for critical values. We have no critical values for this function on the specified domain. We're done with CV. Now we're going to go to E. We need to specify part 2 what the endpoints are. Okay, so our endpoints are, let's go back to the original problem. Where is it? Negative 2 and 3. So our endpoints are x equals negative 2 and x equals 3. Part 3, we want to look for the potential extremas. Potential extremas. Now, when we're talking about extremas, we're talking about minimum and minimas and maximas, okay? out of those ones, we can find out what the um, absolute are by basically comparing them with our check step. So for potential extremas, we're looking for the combination of critical values and endpoints. So our potential extremas, let's specify what we're doing. Critical values and endpoints. So our potential extremas are simply x equals -2 and x equals 3. Why? Because we have no critical values, so only the endpoints determine what our potential extremas are. Okay, now we're going to move on to the next part, which is CVS. S is for the sine chart. We're going to use the sine of f prime to inform us as to what the behavior of f is around the endpoints. Okay, so let's go ahead and do the sine chart part. Now remember your fun charts. Okay, FUN, and then f prime is increasing, decreasing, and then f is increasing, decreasing, plus, minus, and then f double, plus, minus, and then we have no connection here. Alright, so this is what we're going to be using. So let's go ahead and set up our interval. We have a number line, endpoints included. So we're going from -2 all the way to 3. Okay. Let's just put the line here. In this particular problem, we have just one region, one interval, which is namely between 2 and 3. So what we're doing in this problem is we want to see the connection between the sine of f prime and the behavior of f. Okay, so underneath here we're going to determine what the sine of f prime is. Okay, and then that's going to tell us, basically we're looking for where is it positive or negative, and then that's going to tell us about the behavior of f. Basically, where is f increasing or decreasing? Okay, alright, so we have all that. Let's go ahead and get started. So we're going to pick a number in this interval, the only interval that we have, an easy number to work with. How about we just pick 0? Okay, so what we're going to do is we're going to look for f prime of 0, which is basically evaluating the derivative -1/3 at x equals 0. -1/3 never changes, so f prime of 0 is -1/3. What we really care about here is just the sign. Okay, so the sign of f prime is negative. What does that tell us? It tells us that f is decreasing on this entire interval. So if you have a function that starts at a point, -2, and descends all the way to 3, what kind of extremas do you have here? When you're descending from a point, this automatically makes this right here a relative maxima. Okay, and it descends down to this point, that makes this a relative min. Alright, so let's go ahead and explain our reasoning, what we just did here on the right side. So what did we just do? Let me use a solid line. Alright, let's start with the first description, this point -2 right here. Now since f prime of x is what? Is negative to the right of the included endpoint x equals -2, what does that tell us? If the derivative is negative to the right of this endpoint, that means that what? It means that f is doing what? F is decreasing from that, from the endpoint. And the conclusion is, if you're descending from a point, that means that the point that you're descending from is a relative maximum. So that implies that x equals -2 is a relative maximum. Okay? It's just like you're on the rooftop and you get off the rooftop. What's the direction? It's gonna head downwards, right? Because of gravity. So that's what's happening here. You're descending from a high point. Okay. Now how about the second point, 3? Since the derivative f prime of x is negative to the what? To the left of the included endpoint, namely the right endpoint, x equals 3 is the endpoint we're talking about. What's happening with f if f prime is negative to the left of that endpoint? Well, it means that f is decreasing or descending to, is decreasing to that endpoint, decreasing to the endpoint x equals 3. And what does that tell us about this endpoint? If you're descending to an endpoint as like you're heading to the ground, what does that make it? It makes it a minimum, a relative minimum. Okay, so that implies that x equals 3 is a relative, or local is a relative minimum. Okay, so that's just an explanation of how we know that this is a relative mean and this is a relative maximum. Alright, so what we're going to do now is we're going to go ahead and do a check. Alright, so the last part is to check. Part 5 is the check part. So let's check to see what our extremas are. So we're going to start with the first one, our relative maximum, which is -2. So we're going to start with evaluate the function. So let's write down what the original function is. F of x is 4 minus 1/3 x. So we're going to look for f of -2. Plug that in. What do we get? 4 minus 1/3 times -2. And then we have 4 minus times minus is plus 2/3. And then write this as a fraction. And then multiply by 3 top and bottom. We have 12/3 plus 2/3, which is equal to 14/3. Okay, now let's take a look at the other one, f of 3. Our claim is that this is the absolute minimum or the relative minimum, right? So we have 4 minus 1/3 times 3, and then we have 3 times 1/3 is just 1. 4 minus 1 is 3. Okay, so if you want to write 3 using as an equivalent fraction with 9 as the, with 3 as the denominator, 3 is the same thing as 9/3. So you can see the comparison here. All right, so since the function is just strictly decreasing from this point to this point, it follows that this relative maximum here is also an absolute max, and this relative minimum is also an absolute min because the function does not descend below this point. Alright, so it just descends starting from -2 all the way to 3. Alright, and then we can see that this is the maximum and this is the minimum, the absolute max and absolute min. They're also the relative. Okay, so we have the absolute, we have an absolute maximum of y equals, or let's use f of x, of f of x equals 14/3 at x equals -2, and we have an absolute min of f of x equals what, 9/3, and that happens at x equals 3. Alright, so there goes our absolute extrema, namely our absolute maximum and absolute minimum.